Okay, so welcome back to another session of this live sessions for technologies for clean and renewable energy production. I I hope I am audible and the screen is visible to everyone. So let's move on with today's session. Focused on the renewable energy around the world and the consequent slides we were trying to discuss about coal with regards to its production, use, and so on. And in the last class, we discussed a bit about petroleum, mainly the crude oil distillation, different varieties of treatment like hydro treating or visc breaking or various cracking processes and so on. So we looked at solid based fuels, we looked at the liquid based fossil fuel. So in this class, we'll be looking at gas-based fuels or gaseous fuels. You know, things like natural gas, for example. So this week's lecture by Professor Mandal mainly focused on how we can derive a different types of gases, gas-based fuels, gaseous fuels, basically. How to put these gaseous fuels to good use, and what are the different typical end products or end uses of these gaseous fuels. So that was the main focus of the lectures of week 5. So yeah, these were mainly the contents of the starting of the lectures for this week. So Professor Mandal, in detail discussed about the different types of gaseous fuels and the properties of gaseous fuels, and regarding naturally available gaseous fuels, mainly something like natural gas, and what are the different applications of these gaseous fuels. So one application of these gaseous fuel is to just produce heat, or you can use them to produce electricity. And on top of these heat and electricity uses, we can also use them to produce different types of chemicals. Mainly hydrogen, various hydrocarbon based chemicals, and even liquid fuels. So we'll just briefly look into how the lectures went this week, and we'll go. We'll look into some of the previous year's assignment questions as well. So yeah. So gaseous fuels. So gaseous fuels are basically those that burns in the presence of air, mainly oxygen that is present in air. So gaseous fuels burn in the presence of air or oxygen and releases heat. So these are actually considered to be more cleaner compared to solid or liquid fuels, and most of the cases they even have high combustion efficiency and calorific value. So some of the end uses of gaseous fuels can be something like a liquefied petroleum gas (LPG) that we use in our households for cooking, or liquid fuels such as kerosene. And generally, these gaseous fuels are transported by using a network of pipelines. So you must have heard about the different pipeline projects that are undertaken by the oil companies in the country, like IOCL and HPCL and so on. So transportation of these gaseous fuels across the country from different places to places are usually made feasible through a network of pipeline. So gaseous fuels, we can broadly classify them into four. First one, naturally available gaseous fuels. These are the gaseous fuels like natural gas or compressed natural gas or liquefied natural gas. So basically, natural gas derivatives. And then, coal bed methane. So these are methane that are associated in coal beds that are found under the surface of the earth. And then gas hydrates. And then you can also produce these gaseous fuels from solid fuels like coal, for example. Something like a water gas, producer gas, or coal gas, and syngas. So each of these gases are produced by slightly different methods, and each of these gases will also have different composition based on the method that they are produced. So that is one thing. And then you produce these gaseous fuels from petroleum as well. So we notice that the first fraction or the most volatile fraction from petroleum fraction will be C C2 to C5 basically, and these fractions are often termed as naphtha, but a fraction with mainly butane or C4. This fraction is what is called as LPG or liquefied petroleum gas. So this LPG is the one that we use for cooking at our households. And you can also produce these gaseous fuels from biological process or biotechnological process, like produced from fermentation and composting and so on. So biogas is uh, is a renewable gas that we produce from waste biomass basically. And this has found interest in the last few decades due to their renewability. And then you have these landfill gases as well, which are produced from landfills. So these are just some of the classifications of gaseous fuels. So just some stats on gaseous fuels. So 87% of the global energy consumption depends on fossil fuels, including gaseous, liquid, and solid fuels. And natural gas, which is mainly methane, approximately accounts for 21 percentage of the world's energy consumption. And we have approximately 185.7 trillion cubic centimeter of natural gas reserves around the world. Coal bed we have 17 trillion cubic meter, methane gas hydrates in 3 trillion meter cubes, and methane or biogas from animal husbandry also uh, forms this usage pattern. So typically these are the composition of the different gaseous fuels. So natural gas mainly the composition is mainly methane along with some impurities like inerts and hydrocarbons. And then LPG, the major component here is butane, which accounts for nearly 80% of the LPG, and the remaining 20% can be propane. And then we have coal gas, where the major components are hydrogen and methane. And then we have producer gas, where the major compounds vary between hydrogen, carbon monoxide, and carbon dioxide. And they also have a huge amounts of nitrogen as well. And then we have syngas, one of the most important gases that is produced which are heavily used in industry as well as for various other applications. So this syngas mainly consists of hydrogen and carbon monoxide. And then you have trace amounts of methane, carbon dioxide, nitrogen, hydrogen, and so on. Hydrogen, water, basically. Yeah. And then you have water gas, which accounts for mainly hydrogen, carbon monoxide, and some amounts of hydrocarbons, saturated as well as unsaturated. and their typical heating values are also given in this table. So we can see, the natural gas and LPG are accounts for the highest calorific values among these different gases that are produced. So these gases, so for example, if you look at this LPG or CNG and so on, all these gases are usually in compressed nature. Why we are compressing these gases? That means it is if we compress the gases, the volume of the gas will become low, and we are able to contain them in small containers, instead of if we just try to contain them in containers as its gaseous form, the volume would be very high. So for example, if we can compress 100 liters of this natural gas to produce 1 liter of this CNG, this will still give you the energy that 100 liters of natural gas gives you, but you only need a 1 liter container to contain this 1 liter of compressed natural gas. So that is something that is very important in these gaseous fuel industries. And in the compressed air industry, dew point is always an important measure of water content that is present in the gaseous fuel. So sometimes this in industries, this water content can also be termed in the terms of pounds of moisture per million standard cubic feet. So dew point often refers to hydrocarbon dew point, and it is the temperature at a given pressure at which the hydrocarbon components of any hydrocarbon rich gas mixture, such as natural gas, will start to condense out of the gas phase. So the temperature at which a gas will start condensing to form the liquid phase, that temperature is termed as dew point or hydrocarbon dew point. And this hydrocarbon dew point or HDP is a function of the gas composition and pressure. So based on the pressure that we are applying and based on the composition of gas that we are using, whether it's natural gas or syngas or so on, the dew point will also vary for the gas. So some of the applications of gaseous fuels, as I mentioned, we can use them to produce, electricity and heat. We can use them to produce a different variety of chemicals, mainly liquid fuels as well as hydrogen. And there are different types of chemicals that we can produce. So liquid fuels, basically, hydrocarbon-based fuels, and we can use this gaseous fuels to produce chemicals like methanol, DME, and hydrogen. So this is a flowchart of production of electricity by using CNG in the industries. So there are two streams by which we can produce electricity from compressed natural gas or CNG. So the CNG is first taken and sent to a combustion chamber where compressed air is passed into the chamber and the CNG is combusted. And we have the hot flue gas which enters a gas turbine. And then this gas turbine will be connected to an alternator and we can produce electricity from the gas turbine. And the hot flue gas that exits the gas turbine is then sent to a boiler, wherein this boiler is also supplied with water. So because of the high temperature of the flue gases, the water will be converted to steam, and the low temperature flue gases are vented out from the boiler, and this steam is sent to a steam turbine, where then the steam turbine is connected to an alternator and again we can produce electricity. So this is just a basic flowchart of how electricity is produced from compressed natural gas. Then apart from compressed natural gas, we can, as I said, we can also produce chemicals from natural gas. And one of the most widely used method of production of this chemicals from natural gas is reforming. So in a reforming process, natural gas is mainly converted to hydrogen and carbon monoxide containing syngas by a means of either an exothermic or endothermic reaction. So normally we use different types of catalyst for performing this reforming process, and the elimination of oxygen from initial fuel mixture is also important in order to improve the efficiency by minimizing energy losses from catalytic combustion. And the end product can also be used for different applications such as heat, steam, liquid fuels and chemical synthesis. So basically methane can be reformed via various different reforming processes to produce syngas, and then the syngas can be used to produce either chemicals by, let's say, something like a method called Fischer synthesis, or to produce fuels, or to produce hydrogen, and so on. So that is about the reforming process. And as I mentioned, there are different types of reforming processes. So the first one is steam reforming, then we have partial oxidation, and then we have autothermal reforming. So these three are widely used in industries. So the technologies of these three reforming processes are well established, and the other four, it's it's basically under development stage, I would say. So these are innovations to minimize greenhouse gases emissions, to minimize energy consumption, and to improve the reforming process yields. So we move to the first reforming process, which is the steam reforming, or SMR. So in steam reforming, basically what we do is we pass. So I'll show you a flowchart first. Yeah. So this is a steam reforming reactor basically. So in a steam reforming, what we basically do is we pass methane and steam together in a furnace, and this steam, basically H2O, will react with the methane to form various different chemicals, mainly hydrocarbons, or sometimes it can also be hydrogen and so on, depending on what we need. But in steam reforming, yeah, so yeah, again we go back to the first page. So see, you can see this reaction here. Methane is passed with steam in the reactor to produce carbon monoxide and hydrogen. So these are the different types of reaction that can happen in a steam reforming process. So methane can react with water to produce carbon monoxide and hydrogen. Methane can react with two molecules of water to produce carbon dioxide and four molecules of hydrogen. And this carbon monoxide can also react with water or steam to produce carbon dioxide and hydrogen. So this third reaction is called water gas shift reaction. Water gas shift reaction. 298 in delta H. Yeah, so this is the temperature at which this enthalpy is calculated basically. So and like this is a thermodynamic term basically. So delta H is the enthalpy, and this 298 is basically at 298 Kelvin. Right. Yeah. So these are the different reactions that happens in a steam reforming process. And in a steam reforming process, usually the hydrogen is to carbon monoxide ratio is obtained between 3 to 5. And the operating conditions are basically 700 to 850 degrees Celsius and 15 to 30 bar pressure. So as I previously mentioned, steam reforming is a catalytic process. So it can occur without catalyst but requires very high temperature. So normally we use modern steam reforming catalysts such as nickel on ceramic support with or without promoters or stabilizers. Or sometimes we can also use catalyst based on nickel based catalyst and so on. So these precious metals offer alternative to nickel catalyst, and yeah, the supports must be strong, inert, and thermally and chemically stable. So some of the commonly used supports are something like gamma alumina, or something like, so I don't know whether you have heard this catalyst nickel on gamma alumina. So this is basically a nickel catalyst on the support gamma alumina, or we can use ceramic supports as being used here uh, in this modern steam reforming catalyst. So nickel can be used on ceramic support with or without promoters for steam reforming process. Right. Then we move on to the next process, which is partial oxidation. So partial oxidation, as the name suggests, it's basically partially oxidizing the methane to produce hydrogen. Right. So there are two different routes by which you can achieve this. The first is the direct route, wherein you just add methane to half molecules of oxygen. So basically this is less than stoichiometry, stoichiometry for complete combustion. So this kind of less than stoichiometric requirement for complete combustion is something that we have also seen in gasification, where gasification is also basically partly combusting the solid fuels or gaseous fuels, I mean liquid fuels. So here that's what we do. We partially combust this methane to produce carbon monoxide and hydrogen. Then the other route is a two-stage route, wherein first we completely combust this methane with two molecules of oxygen to produce carbon dioxide and water. And then methane is again passed down to this carbon dioxide and water, wherein methane will react with carbon dioxide to give carbon monoxide and hydrogen, and the methane will react with water to give carbon monoxide and 3 hydrogen. So these are the two different routes by which we can partially oxidize methane to produce carbon monoxide and hydrogen, or basically syngas. So this CO plus H2 is basically termed as syngas. And some of the catalysts that are used are transition metals and precious metals like nickel, cobalt, or ruthenium, rhodium, palladium, platinum, and so on. And then we have the third process, which is the autothermal reforming. So this basically combines both steam reforming as well as partial oxidation reforming process. So the reactions I'll show later. So here the hydrogen to carbon monoxide ratio we can achieve up to 2, and the operating temperature is 850 to 1000 degrees, and the pressure is 20 to 100 bar. And we usually use nickel based catalyst for autothermal reforming. So yeah, so this is the schematic representation for this autothermal reforming reactor. So basically what we do is we pass methane along with both oxygen as well as steam. We pass both oxygen and steam. So in the steam reforming, we used to pass steam with methane, and in the partial oxidation, we passed oxygen with methane. Here we do both. We pass both steam as well as oxygen. And then we have two zones here, the combustion chamber and the reforming zone. So in the combustion chamber, what happens is this methane will first get combusted to form carbon dioxide and water and carbon dioxide and hydrogen. And then in the reforming zone, what happens is the remaining methane will react with the water that is formed here, or the steam that we passed inside the reactor, to form carbon monoxide and hydrogen. And the steam and the methane will also react with carbon dioxide that is formed from this combustion chamber to form more carbon monoxide and hydrogen. So that is basically how an autothermal reactor proceeds. By proper adjustments of oxygen to carbon and steam ratios, the partial combustion in the thermal zone supplies the heat for completing the subsequent endothermic steam and carbon dioxide reforming reactions. So the combustion is an exothermic process and this reforming is an endothermic process. So exothermic means it releases heat and endothermic means it absorbs heat. So what happens is the combustion occurs first, which is an exothermic reaction, and it releases heat, and this heat is being utilized in the reforming zone because it is an endothermic reaction. And the final product, you will get the syngas. The product gas composition at the exit of the reactor results to very close to the thermodynamic equilibrium of an adiabatic reactor. So yeah, so now we have produced syngas. As I mentioned, we can use this syngas to produce liquid fuels. And why we want to produce liquid fuels, or either by performing reforming, or by compressing this, because of ease of transportation, basically ease of containing and transportation. So that is one of the major reasons why we try to convert all these gaseous fuels like syngas and so on to its liquid form. And one of the most followed methods for converting gaseous fuels to liquid fuels is the Fischer-Tropsch synthesis. So in a Fischer-Tropsch synthesis, the syngas is first converted to wax, naphtha and diesel, and then this wax can be hydrocracked to produce diesel and other products further. So overall the reaction is strongly exothermic in nature, and it can release about 180 kilojoule per mole. And these are some of the major reactions that occurs in Fischer-Tropsch synthesis. So syngas is basically carbon monoxide and hydrogen. So this carbon monoxide and hydrogen is converted to hydrocarbons basically. So that is the main process that occurs in the Fischer-Tropsch synthesis. So yeah, so to produce paraffins, which are basically straight chain alkanes, this is the reaction. N number of CO will react with 2 N plus 1 moles of hydrogen to form paraffins and water. And if we wanted olefins, olefins are basically double bonded or triple bonded compounds. So to produce olefins, CO can react with two multiples of hydrogen to form olefins plus water. And then we have the water gas shift reaction that also happens in the Fischer-Tropsch synthesis, which is basically CO plus H2O reversibly giving CO2 plus hydrogen. So these are some of the reactions that occurs in a Fischer-Tropsch synthesis. So this is the brief flowchart of the Fischer-Tropsch synthesis process. First, syngas with the gas ratio hydrogen is to carbon monoxide ratio of 2 is to 1 is sent to the Fischer-Tropsch reactor, where we produce the different feedstocks like the wax and diesel, kerosene and so on, as well as some amount of gas. So this is then separated to form the the wax that comes out of it, and some amount of gas goes on top. This wax is then hydrocracked using hydrogen to produce the different feedstock, different product streams such as naphtha, kerosene, distillate, diesel, jet fuel, and other Fischer products. Right. So the Fischer-Tropsch products, Fischer-Tropsch synthesis can occur at two different conditions. It can occur at either high temperature condition or low temperature condition. So in high temperature condition, around 50 to 80% of the hydrocarbons that are produced are having a carbon chain greater than C5, and the wax content is very low, which amounts to around 4%, and the ratio of gasoline to diesel will be 2 is to 1, and the cetane number will be 50 to 60. When it comes to low temperature Fischer-Tropsch synthesis, the amount of uh, compounds with C5 carbon range will be 20 to 30%, but then we have a high wax content of 50 weight percent, and then the gasoline ratio to diesel ratio will be reversed here, 1 is to 2, and the cetane number will be much higher, around 80. So the high temperature Fischer drops are usually carried out in the range of 300 to 350 degrees Celsius, and the low temperature Fischer drop synthesis are carried in the range of 220 to 270 degrees Celsius, and these Fischer drop synthesis are usually carried in the presence of iron or cobalt based catalyst. So some of the routes by which we can produce hydrogen from different feedstocks, mainly like syngas and so on, are as follows. So we can either reform the feedstock, which can either be hydrocarbon or biomass to produce hydrogen. We can gasify carbonaceous feedstocks to produce hydrogen, or decompose hydrocarbons, thermolysis of water, and electrolysis of water. This is also called as water splitting, where we separate the hydrogen and oxygen from the water, and then photolysis, dark fermentation, and microbial electrolysis. So, okay, let's say we have now produced hydrogen from the variety of different processes that we just saw from syngas and so on. This hydrogen can also contain a variety of impurities in the hydrogen stream. And in order to clean or purify this hydrogen stream, we use a process called pressure swing adsorption for hydrogen separation. So in a syngas, as I mentioned it, the gases are mainly CO and hydrogen, and it can also contain very low amount of hydrocarbon impurities in it. So we want to separate this hydrogen from these different streams of gases, and for that we use the process called as pressure swing adsorption, or pressure swing adsorption. So basically, in a pressure swing adsorption, we pass the feed gas, which contains high amount of hydrogen along with some impurities at high pressure, to adsorption columns, wherein the hydrogen is separated to form the pure hydrogen product, and then the remaining gases are vented out, and these gases are called as tailed gas. So there are different types of adsorbents that we can use based on the feedstock gas that we are using. So for example, if we use silica gel, we can separate out ethane, propane, butane, and heavier hydrocarbons from hydrogen stream. If we use activated carbon, we can separate out methane and carbon dioxide. Molecular sieves, we can separate out methane, carbon monoxide, and nitrogen. And activated alumina, we can separate out the moisture or water from the hydrogen gas stream. So yeah, these were the major topics that were discussed by Professor Mandal for this week. So now what we'll try to do is we'll try to solve some of the previous year's assignment questions, and let's see what happens. So what is the approximate percentage of world's energy consumption in terms of natural gas? Okay, just a second. Okay, yeah, sorry about that. There was some issue with the PPT actually. I kind of forgot to hide the answers. So, okay. So, what is the approximate percentage of world's energy consumption in terms of natural gas? Yeah, you saw the answer. It is 21%. So, hydrocarbon dew point is a function of dash and dash of the gas, and the answer here is gas composition and pressure. So identify A, B, C in the given flowchart. So A is here, B is here, C is here. So if you recall the flowchart for the electricity production from compressed natural gas, are you able to recall what A, B, C is? Okay. So the C is the combustion chamber. B is the boiler. And A is the steam turbine. No, I think this is the steam turbine. No, it's yeah, this is correct only. So this is a boiler and this is steam turbine. So the right answer here is A steam turbine, B boiler and C combustion chamber. So option C is the right answer. What are the two major components of syngas? Okay, the major components of syngas are carbon monoxide and hydrogen. So the answer here is option C, carbon monoxide and hydrogen. In modern steam reforming process, the catalyst used is, and based on our recollection, the right answer here is nickel on ceramic support with or without promoters or stabilizers. The reaction carried out in the reforming zone of autothermal reactor is, and if you remember correctly, the reaction was where methane reacted with water to produce carbon monoxide and hydrogen in the reforming zone of the autothermal reactor. So the right answer here is option B, methane plus water giving carbon monoxide plus hydrogen. The hydrogen to carbon monoxide ratio in autothermal reforming is around dash. And we just saw that in the previous slides. The answer here is 2. The ratio of hydrogen is to carbon monoxide will be 2 is to 1, or this hydrogen to carbon monoxide ratio is 2. For low temperature Fischer-Tropsch synthesis, the cetane number of the product is nearly dash. So that also, okay. So that also we saw in the previous PPTs. For high temperature Fischer-Tropsch synthesis, the cetane number was between 50 to 60, and for low temperature Fischer-Tropsch synthesis, the cetane number can be around 80. So the right answer here is option D, 80. What product is taken out other than hydrogen in the pressure swing adsorption process for hydrogen separation? So in the pressure swing adsorption, we pass the gases, hydrogen along with the impurities, which can be, CO, hydrocarbons and so on, and we send them to the adsorption columns wherein pure hydrogen is separated out and the bottom product is called as tail gas. So the right answer here is option B, tail gas. Final question of the day. The gas produced by a steam reformer is exiting at a pressure of 2100 kilopascals and has the following composition. Determine the partial pressure of each component. So we have hydrogen, water, carbon monoxide, carbon dioxide and methane along with its mole fractions. We want to determine the partial pressure of each of these components. So how do we do that? We use the formula. So you must have heard the formula where the total pressure into mole fraction of component, let's say I, will be the partial pressure of component I. So this is a formula I think you must have heard from your school days as well as in your BTech classes as well. So the partial pressure of any component I in a gas mixture can be given by the total pressure of the gas mixture into mole fraction of the component I in the gas mixture. So this is exactly what we'll also be doing here now. So for example, the partial pressure of hydrogen can be the total pressure of the system into mole fraction of hydrogen. So the total pressure is 2100 into mole fraction, that is 0.392. So partial pressure of hydrogen will be, if we do this multiplication 2100 into 0.392, it should come somewhere around 823.2 kilopascal. In a similar way, we can also do partial pressure of water. This will be 2100 into 0.438 and that will be 919.8 kilopascal. And then we have a partial pressure of carbon monoxide, which will be 2100 into 0.081 and that will be 170.1 kilopascal. And partial pressure of carbon dioxide will be 2100 into 0.08, and that will be 168 kilopascal. And partial pressure of methane will be 0.2100 into 0.009, and that will be 18.9 kilopascal. So out of these four options, option A is what is matching with this answers that we get. So option A is the right option for this question. So the partial pressure of hydrogen will be 823.2, partial pressure of water will be 919.8, partial pressure of CO will be 170.1, partial pressure of carbon dioxide will be 168, and partial pressure of methane will be 18.9 kilopascal. Right? Okay, I hope you understood how we did this numerical problem. So I think similar question is also done in the tutorial class of the lectures. Please do go through the lectures. And again, I'm just reiterating that this live session is just supposed to be a doubt clearing session, or just a recap or overview of what Professor Mandal is teaching in the lectures. Please do go through the lectures Professor Mandal is teaching in the NPTL, and use this live session as a supplement to those lectures rather than the replacement of those lectures. Right? So I think that's it for today. We'll stop at this point. So yeah, if you guys have any doubts, please you can unmute yourself and speak, or if you want, you can always type in the chat box. If you don't have any doubts, I guess that is it for today's class. Yeah, hope to thank you for joining, and hope to see you guys next Sunday. Yes, go ahead.